We lose horsepower as we go up a hill due to changes in air density. So at sea level, we have a column of air above us that reaches up 500 kilometers. That 500 kilometers of air is pressing down on us at the bottom here, which creates a pressure of 14.7 psi. Then as we go up a hill, the column of air is obviously smaller. As it's smaller, it's now got less weight pressing down, so we have less compact air. G'day, I'm Trav, and welcome back to the Fast and the Nerdy. We lose horsepower because of the lower density for two reasons. The first one is that as the piston comes down, we create a larger volume in the combustion chamber. This larger volume means it's now at a lower pressure than atmospheric pressure. Then when the valve opens, we can see that the air is going to rush in and fill that void and then equalize the two pressures. The higher that we go, the less pressure we have in here, so the less it's going to want to rush in, and also the less compact the oxygen molecules are. We get less oxygen for a given volume of air flowing in. Engines operate on a strict fuel ratio. For a given volume of air, it needs a given volume of fuel. We have less air, so it's going to make less fuel. Less fuel and air means we're going to have less of an explosion. Less of an explosion means we're going to have less horsepower. To get an idea of the amount of horsepower we're going to lose, we just use the ideal gas law, which is the pressure multiplied by volume is equal to the number of moles of gas multiplied by the ideal gas constant multiplied by temperature. Number of moles of gas is equal to mass divided by molecular weight. Sub that in, rearrange it. Mass over volume is equal to density. So this here is equal to density. And then we know that the molecular weight and the ideal gas constant are both just constants, so we'll just remove those. And then if we set this calculated density over the original density we had when we got our original horsepower figures, we can create a ratio which we multiply by the original horsepower figures, and we get an idea of how much horsepower we've lost. As an example, if you want to see the impact that 1,000 meters has on horsepower, we can get the density at 1,000 meters, divide that by the density at sea level. That's where we recorded the horsepower figures. The pressure at 1,000 meters is 89,996 pascals. Divide that by 15, that's 15 degrees Celsius, plus 273. Divide that by the pressure at sea level, which is 101325. Divide again by the same temperature, and we get 0.89. So if we had 100 horsepower at sea level, we now only have 89 horsepower at 1,000 meters. And if we do this over a range of temperatures and elevations, so different pressures, we get the following map. Here you can see a map of the percentage of horsepower that we have. So the one figure is at 15 degrees and at sea level. It's where we recorded our horsepower figures. We can see here that temperature has an impact on the density of air and therefore our percentage of horsepower. Colder we go, the more dense the air, the more horsepower we have. But the big thing is the elevation. So the higher we go up, the less dense the air, the less horsepower we have. And if we got really unlucky and we're up at the 4,300 meters up and it somehow was 35 degrees, we would only be at 58% of our total engine horsepower. So you can see using this map that one thing we can do to increase horsepower or make sure we have as much horsepower as we can is to reduce our under bonnet temps and especially our intake air temps. So the lower the temp we can get that, the more percentage of horsepower we have. Another thing we can do is remove any restrictions we might have in the intake manifold, helping us get the full 14.7 psi at sea level at the intake valve. But the best thing we can do is to increase the density of the air, and the best way to increase the density of the air is to add a turbo.